Let us practice the implicit function theorem on the following example. Consider the equation x cubed plus y cubed minus 3xy minus 3 is equal to 0. Near the point x0 is 1 and y0 is 2. So the question is whether this equation defines a function small f relating x and y, and if so, what is the function value at 1? What is the first derivative at 1? And what is the second derivative of the function small f at 1? This is question mark, right? Not 2. And if we have the second derivative, we can write the Taylor polynomial of order 2. So first, let's denote the left-hand side as a function capital F. This will be a function of two variables, and we just copy the formula on the left. X cubed plus y cubed minus 3xy minus 3. This function is continuous at this point. Actually, it's continuous everywhere, and as a polynomial, it has derivatives of any order. So the best thing is f is in C infinity R2, because we have two independent variables. This is a function of two variables, and it is given by this explicit way. The function small f will be a function of one single variable and given only in the implicit way, no explicit formula. First, we want to check whether the point 1, 2 satisfies this equation. So if x is 1, this is 1. If y is 2, this is 8. Minus 6 minus 3 is 9 minus 9, which is indeed 0. That's good. That means the point does lie on this curve. And then we want the derivative with respect to the variable that we want to declare dependent, y in this case, to be different from 0. So we compute the partial derivative of capital F with respect to y. I sometimes use also this notation. And this will be 0 plus 3y squared minus 3x. And we evaluate this derivative at the point 1, 2. If y is 2, we have 12 minus 3, which is 9, and this is different from 0. That's good, because then, using these three results, f is continuous and has derivatives, the function value is 0 at this point, and the derivative at this point is from 0. That means such a function y as a function of x does indeed exist. So let's find the function value and the first and second derivative. Well, the function value, this is easy. This is this point 2. You see, we don't have the formula for small f, so we cannot evaluate f at 1. But this is the second coordinate, the y coordinate of this point. What about f derivative? We have two possibilities how to find the first derivative. Either we can use the formula that it is minus derivative of capital F with respect to x divided by the derivative of capital F with respect to y. We have fx here, fy here, so we prepare also fy. We have fy, so we prepare fx. We which is 3x squared plus 0 minus 3y. Now we can write the derivative minus effect is here 3x squared minus 3y divided by fy, which is 3y squared minus 3x. We can reduce 3 and we have minus fraction x squared minus y divided by y squared minus x. And we can evaluate the derivative at x is 1. But again, you see, this information alone, that x is 1, is not enough to evaluate this formula. We also need the information about y, which is 2. So we have minus fraction 1 minus 2, which is minus 1, divided by 4 minus 1, which is 3. So the derivative is 1/3. Well, this is already quite useful information. It tells us that the function small f has definitely no extremum at 1, because the positive derivative indicates the function is increasing. No extremum, no minimum, no maximum at this point. So that was one way how to find the first derivative. Another way, sometimes is quicker, sometimes is more difficult, that we take the equation and we differentiate with respect to x, looking at y as a function of x. So once again, if we copy the equation here, x cubed plus y cubed minus 3xy minus 3 is 0. And now we look at y as a function of x. So we differentiate 3x squared plus 3y squared times y derivative. This is the derivative of the inner function, because this is a composite function. Minus 3, and the product xy can be differentiated when we differentiate x, which is 1, times y, plus x times y derivative minus 0 is 0. We can divide by 3 to arrive at x squared plus y squared y derivative minus y minus xy derivative. And now substituting 1 for x and 2 for y, we can find y derivative. Namely, x is 1, so we have 1, plus y is 2, so we have 4y derivative, minus y is 2, minus x is 1. That means 3y derivative is equal to 1. That means y derivative is equal to 1/3. Well, this is in perfect agreement with our previous result. Note that when we substitute the values for x and y, then this is the derivative at x0 is equal to 1. Well, you may ask, why do we write x alone? Why don't we write xy when the formula depends on y as well? Formally, f is a function, small f. Small f is a function of just one variable. And so are all its derivatives. Just function of one single variable. Well, we have this formula, and to evaluate the formula to get the result, we need y. But the function f is, and all its derivative is the function of just single variable. So we write x alone here, even though x alone, information alone, is not enough. So that was for the first derivative. Now let's have a look at the second derivative. We can either differentiate this expression that was f prime. If we differentiate this expression, we have f second, and the derivative is the minus fraction y square minus x square. And now derivative of this, which is 2x minus y derivative times the denominator y square minus x minus x square minus y times the derivative of the denominator, which is y square, the derivative is 2y derivative minus 1. If you are confused by y prime, you can write small f instead of y, if it helps you. Well, and then we can evaluate this at the point x is 1, y is 2, and f derivative or y derivative is 1/3. And then we have f second at 1. Once again, we write just x, even though to use this formula we need x and y derivative. Minus fraction 4 minus 1 is 3, square is 9, and here we have 2 minus 1/3 times 4 minus 1 is 3 minus 1 minus 2 is minus 1, so plus 2y square is 4/3 minus 1. So we have minus fraction, and here we have 5 plus 1/3 divided by 9, which is minus 16 divided by 27. So this is the second derivative of the function small f at the point 1. Alternatively, again, we can find a second derivative by differentiating this equation twice. Here we have the result after differentiating for the first time. Then we divide it by 3, and we have this formula. If we differentiate this once again with respect to x, then we get condition for the second derivative. Let us do this and to compare whether we get the same result. Derivative of x squared is 2x. This is a product. Derivative of y squared is 2y derivative times y derivative plus y squared, and the derivative of y prime is y second, minus derivative of y is y prime minus, we differentiate x, and we copy the second, minus, we copy x, and we differentiate y prime, which is y second. And derivative of 0 on the right is 0. Now, when we use these three values, 1 for x, 2 for y, and 1/3 for y prime, we can evaluate the second derivative. Let's do this and let us compare this result with our previous result. So we have 2 plus 4 divided by 9 plus, and here we have 4 y second minus y second, which is 3 y second, minus 1/3 is minus 2/3. That means 3y second is 2/3 or minus 2 plus 4, 9 minus 6 over 9. This is 2 minus 2 over 9. No. Sorry, let me check this. 3y second is minus fraction 2, 4, 9, minus 6, 9, 2, minus, yeah. So 3y second is minus 16 over 9, and then y second is minus 16 over 3 times 9 is 27. Yeah, which is the same as before. So we have seen two ways how to find the first derivative and two ways how to find the second derivative of a function for which we have no formula, just implicit definition. Well, before we stop here, if we have the first and the second derivative, we can write the Taylor polynomial. This is the function value, which is 2, plus the derivative, which is 1/3, times x minus x0, plus 1/2 of the second derivative, that means y minus 1/2 of 16 is 8, over 27 times x minus 1. So you see we have the second order Taylor polynomial for a function for which we have no formula. And in this way we could evaluate the derivative of any order. So we can write the Taylor polynomial of any order. Can we sketch the graph of f? Unfortunately, not the complete graph, but only a small piece in some neighborhood of the point 1, 2. The function is increasing because the derivative is 1/3, but only slightly. And the second derivative is negative, so it is convex down. something like that. Well, and what happens here, we don't know yet. This is just a property of the function in some close neighborhood of the point given. So this is the Taylor polynomial, and this is a small piece of the graph of the function, small f.